about to describe an idea that is so simple that at first it might seem hard to understand. The trick here is to think of this in the simplest possible manner. The speed of light is equal to 299,792,458 meters per second. Right now, physicists define the speed of light as 299,792,458 meters per second. However, using the speed of light definition of time, things change. While time is our standard of motion, a length of time is a length. 1 second equals 299,792,458 meters. Thus, 1 second is a distance physically equal to 299,792,458 meters. 1 little second is exactly the same thing as that huge distance. Do not make this hard. This is easy. Simple. When I say they are equal, that is all I mean. They really are equal. Every specific unit of time has a specific equivalent distance. For example, 1 second is equal to 299,792,458 meters. 2 seconds is equal to 599,584,916 meters. 1/2 of a second is equal to 149,896,229 meters, and so on. Understanding time leads us to a new way of measuring motions. Right now, people think in terms of things like miles per hour, kilometers per hour, and meters per second. People think in terms of distance divided by time. Simple. Instead, in this new physics, we will think in terms of how far an object moves divided by how far light moves. If needed, take some time, pause the film, and think about this. This is easy, and it is hard. It is simple, and it is complex. To correctly measure something's motion, you take the distance the object travels and divide it by the distance light travels. As a result, now we will measure motion in terms of things like meters per meter, miles per mile, and kilometers per kilometer. The measurement of motions will become the ratios of two distances: the distance the object travels divided by the distance light travels. This alone is a major change in physics. This specific change is the most obvious difference between traditional physics and this new type of physics. Most people believe time is one-dimensional. It is not. Time moves in all three dimensions of space: up and down, left and right, forward and backward, at the same time. Without going into all the complexities and possibilities, the simplest way to think of this is just to think of time as an expanding sphere of light. Here's an animation that has 3 expanding spheres. At the start of the animation, each sphere is a different size, but each is expanding at the same constant quantity of motion. Imagine they are all expanding at the speed of light. If you've never thought about this before, then this next simple idea might blow your mind. A key detail here is the origins of any two spheres expanding at the speed of light cannot move with respect to each other. In this example, the origins of all 3 spheres are motionless. The origins of any expanding sphere of light defines a reference frame that is at absolute rest. Let's look at that animation again. Again, expanding spheres of light define absolute rest in space. Ponder this idea. Decide for yourself. Am I right or am I wrong? Can two expanding spheres of light have a relative motion? If it is possible, then the following animation would be possible. Let's look at that animation again. Here, the center expanding sphere is moving. The direction of motion doesn't matter. At the beginning of this animation, each sphere is the same size. Supposedly, each is expanding at the speed of light. However, I say supposedly because the animation depicts the center blue sphere as if it were moving to the left, above the magenta sphere. If this were possible, which it is not, then parts of the sphere would be moving faster than the speed of light. This is just impossible. It is simply impossible to move an expanding sphere of light away from its origin. Obviously, I am right. It is simply impossible for any two expanding spheres of light to have any relative motion. Here's that animation again. This animation is only possible if the spheres are expanding slower than the speed of light. Now, imagine a slightly different scenario. Imagine we replace the three expanding spheres of light with three traditional clocks. Instead of defining time to move at the speed of light, we use some slower motion. Let's look at that animation again. If we use traditional clocks, using the motion of the sun, or an hour hand, or a minute hand, or a solar second, or the motion of atomic second, then this animation is possible. If time is defined to move at a slower motion than the speed of light, then your clocks can have relative motion. In this case, Einstein's relativity is required in order to equate the motions on the clocks. After all, they have different motions. When your clock moves at the speed of light, then you only have one definition for time. That is nice. One clock, one motion, and it works in every reference frame. Someone might argue, well, what if you can travel faster than the speed of light? Fine. Then time would be redefined to travel at that faster rate. As I mentioned earlier, this means time travel is impossible by definition. Personally, I love time travel stories. Unfortunately, time travel is impossible. In order for time travel to be possible, every aspect of the universe must be able to stop and reverse its direction of motion. Even if it were possible to somehow make one photon of light stop and reverse its motion without coming into contact with anything, which is something that is not possible, it would still be impossible to signal every photon in the universe to stop, reverse direction, and continue traveling at the speed of light in the opposite way. For example, how would you communicate with photons of light on the other side of the universe? Someone might argue, just think, stop, go backwards now. No, unfortunately, time travel is just one of the many fantasies that is easy to imagine. Time travel will always be impossible. Remember, whenever somebody tells you that Einstein's theories of relativity prove all motions are relative, think of these animations and remember, they are wrong. Everything is not relative.